Hello and welcome to Sidense's webinar on selecting NVM memory for the smart connected universe. Our speaker today will be Andrew Faulkner, Senior Director of Product Marketing with Sidense. Andrew has held senior marketing and product line management positions at several leading companies, including Xilinx Semiconductor, International Rectifier, and Texas Instruments. He holds an MBA from the Open University and an HND in Electrical and Electronic Engineering from the University of Central Lancashire. Please welcome Andrew Faulkner.
Hi, thank you, Sean, for your introduction. And a big thanks to all of you for joining us today. I hope you found it useful. If not, you can always see me after for a refund. Okay, before we start, let's quickly sketch a brief outline of today's presentation. I'm going to spend around 30 minutes total discussing on how one-time programmable memory, or OTP, can help you in the design of cost-effective, secure, and reliable solutions for a vast array of applications that are part of what Sidense refers to as the smart connected universe. We will start with a few words about Sidense, establish a working definition for the smart connected universe, consider the range of NVM options, and then move on to develop an understanding for some of the key design considerations when choosing an NVM solution. We will conclude with a discussion on how OTP, particularly Sidense OTP, can be a source of competitive advantage for your next smart connected design. I hope that sounds okay. Okay, Sidense develops and sells intellectual property, IP. Sidense IP is a type of non-volatile memory commonly referred to as one-time programmable memory, or as I said before, OTP. Sidense has been a trusted memory partner since 2004. In fact, last year, 2015, we celebrated our 10th year anniversary. Financially, Sidense is performing extremely well, posting a record revenue in the last fiscal year and 45% annual compound growth rate over the last 3 years. With the backing of stable, long-term investors, Sidense is well-resourced with an extremely focused and dedicated workforce, currently around 65 and growing. Over 80% of these are employed in an engineering capacity. Sidense is well regarded for its customer support, providing global support from its offices in North America, Asia, and Europe. Further, Sidense is engaged with over 130 customers worldwide and has over 400 design-ins, many of whom are leading tier chip suppliers. Our OTP technology is well proven in many high volume applications and is protected by over 120 patents. Okay, let's define the smart connected universe. The smart connected universe is a term used at Sidense to describe a collection of market segments that are both smart, having some computational capability, are connected, typically wirelessly. They also share a common set of requirements in terms of cost, power, and performance. This new segment cuts across several of the more traditional market segments and includes mobile computing, IoT, wearables, automotive, medical, and industrial. Quite a cut across these segments. Products sold into these segments represent a huge opportunity for chip suppliers and by default, IP suppliers like Sidense. At Sidense, we're focusing on specific chips that derive the best benefit from the Sidense approach in terms of low power, cost, efficiency, reliability, and security. Such chips, many of which are found in today's smartphones, include, but are definitely not limited to, power management ICs, PMICs, touchscreen controllers and display drivers, MEMS smart sensors for environmental sensing and motion, NFC near-field communication and combo wireless, auto multimedia, wireless charging, and many more, as we'll see later. Okay, so what does a system within the smart connected universe look like? Typically, there will be edge nodes, hub nodes, and compute nodes. If we work from the left to right, the edge node operates in the analog, in the human domain, that's where we all live, and gathers data from sensors that detect, and detect is noted by the D, a variety of things such as environmental conditions, levels, motion, or even image. The amount of smarts or computational ability will vary from dumb sensors with no to little smarts, or sophisticated sensors containing MCUs, analog conditioning circuitry, and combo wireless transmitters receivers. Nodes communicate, as indicated by a C, between each other using a variety of wireless technologies, including Wi-Fi, Zigbee, Bluetooth, Z-Wave, cellular, or even a combination. Data from several edge nodes are aggregated at the hub node, where sensor information is combined in a process called sensor fusion. Aggregated data from hub nodes is then sent to the compute node, usually in the cloud, for processing and further decision making. Incidentally, as well as representing smarts, S could also represent security, which is taking an ever-increasing importance in the smart connected universe. Also, as we move from the left to right, everything gets bigger. The amount of smarts required, the level of security, as well as the dollar value. Edge nodes can cost sub 50 cents for simple temperature sensing thermistors, while at the other extreme, compute nodes can be expensive server equipment costing millions. By the way of an example, let's consider a wearable like Wahoo. And as a keen cyclist, I'm very familiar with this application. At the edge node, you'll find the crank and speed sensors and the heart rate monitor. The hub node in this case is your smartphone that aggregates the data, while the compute node is in the cloud providing networking and services. Okay, let's have a look at the size of the market. This chart was provided courtesy of IHS and shows the projected growth for IoT devices, which is an important segment within the smart connected universe. The number of interconnected devices globally is projected to expand very, very quickly to over 50 billion devices by 2025. To put that into context, that equates to more than 6 devices for every man, woman, and child on the planet. And if you just look in your pockets and see what kind of connected devices you have already, I don't think this will be too much of a stretch. As we can see, industrial, consumer, and communication segments will continue to be the dominant segments. Recent revenue estimates for integrated circuits, ICs, within the smart connected universe will reach around $90 billion. With the total IC market estimated by McLean to be around $290 billion, this pegs the smart connected contribution at around 30% of the total. While currently dominated by smartphones, phablets, and tablets, this mix will change over time. Okay, so now we've established a working definition for our smart connected universe, and we've already seen that typically it includes smarts and also significant digital processing, analog processing, and connectivity. It there follows that there's a need for memory, particularly non-volatile memory. A number of technologies are available for embedding NVM on chip. We're only considering on-chip NVM. The ones we are going to discuss are mask ROM, anti-fuse OTP, floating gate OTP, eFuse, and eFlash. Obviously, you can have external memory, but we're not discussing these today. Let me exchange this chart. The horizontal axis represents the number of times the memory can be written to or programmed, and referred to as endurance. The vertical axis represents the cost of ownership in dollars. Contributing factors are things like area and processing complexity. Inside the axis, or inside the graph, are pie charts representing these key technologies. The bigger the pie slice, the better the performance. Absence of a slice means that there's no support is available. The considerations listed include temperature, power, security, and the ability to program in the field. Okay, now that we understand the graph, let's look at the key NVM types, starting with ROM. ROM is permanently programmed during wafer processing, providing an area-efficient and fast access memory solution. However, changing ROM contents involves mask changes and a fab cycle, introducing both additional cost and, perhaps more importantly, delays in product availability. Embedded flash, referred to as eFlash, may be written multiple times also, and as such is well suited for file storage and other operations where data is constantly being updated. But it also requires extra processing steps to fabricate. Having said that, if flash is already available on chip, say for a microprocessor design, then this may not be a consideration, but a lack of physical security and a limited temperature range may be an issue. MTP, multi-time programmable. This also allows programming multiple times, but again requires additional mask steps. Typically has lower endurance than eFlash. eFuses are also available, both in metal or poly, and are typically supported or supplied by the foundry. eFuses typically are only available for smaller bit counts and also require larger die areas for the same capacity compared to other embedded NVM solutions. Also, in-field programmability can be problematic. Another drawback is that being foundry specific, these are not particularly portable or not portable at all from foundry to foundry. At last but no means least is the OTP, of which there are two types, anti-fuse, which is supported by Sidense, and floating gate. OTP provides a permanent, non-reversible memory that can be programmed only once, hence the name, one-time programmable. It is inherently physically secure, operates over a wide temperature range, and can be programmed in the field. It also has low power properties. OTP offers designers a cost-effective, practical approach for storing data that needs to be saved only once. We will discuss anti-fuse OTP in a little more detail in the coming slides. Okay, so let's assume after reviewing the NVM alternatives, you choose OTP for your next smart connected design. May I say what a wise decision that was. Let's also assume that after further consideration, you choose a Sidense 1T OTP anti-fuse, an even more wise decision and one that you won't regret. There are many attributes to the Sidense OTP bit cell that make it a good fit for the smart connected universe. Firstly, as the name implies, it only uses a single transistor per logic bit. Sidense OTP macros consume very little area, and its programming is precisely controlled and irreversible. Since programming does not involve charge storage for determining bit cell state, like flash, it is highly secure and low power. No additional masks or processing steps are needed to implement the macro. The design is also extremely portable across all nodes, including specialty nodes like HV, BCD, and RF, and also between foundries. It also operates reliably over a wide temperature range, in fact as wide as -40 to 150 degrees C junction, making it suitable for auto-grade applications and harsh industrial applications. So let's have a quick look at the Sidense anti-fuse 1T OTP bit cell. I hope there's no physics majors on the call. So looking at the diagram on the right, the bit cell is formed by a single split channel transistor with thick I/O and thin core oxide regions below the transistor's gate. Applying a sufficiently high programming voltage to the split channel transistor, between 5 to 9 volts depending on the process, the thin oxide breaks down, forming a conductive path between the gate and the channel. In doing so, the bit cell is programmed and its state represents a logic 1. Hence the name anti-fuse. Since a fuse is normally blown open, the anti-fuse is fused closed. The programming breakdown location is precise and only occurs in the thin oxide of the channel. It is non-reversible, extremely reliable, and results in an easy-to-read bit cell with a long-term retention of over 10 years at a maximum temperature and 100% duty cycle. Okay, now let's have a look at where the bit cell fits in the overall OTP solution. This slide shows a typical architecture for a Sidense OTP solution. The solution includes 3 main parts: the memory array, which contains the bit cell we just discussed, an integrated power supply, IPS, and a controller. The memory array consists of multiple bit cells arranged in configurations of varying word sizes and densities. They can be grouped together to form banks or sectors for high-speed simultaneous reads and programming. In the memory array, in addition to the bit cell, will include sensing amplifiers to detect the state, multiplexers, decoders, and simple interface control circuits, amongst other things. The array can also be configured to support a variety of read modes like single-ended, differential, redundant, and differential. These modes allow the OTP to be optimized for area, power, or security. The integrated power supply, known as the IPS, provides all the necessary voltages for reading and in-field programming. If in-field programming is not required, then an external programming voltage can be applied, usually at device test. A range of IPS options and building blocks such as band gaps, regulators and charge pumps are available. This provides the designer with a degree of flexibility to work around the voltage rails already available on his chip. The controller provides high-level control for the macros, simplifying the operation and integration into SoC designs. It provides programming control, self-test features, and error detection correction schemes. Okay, so what are the uses of this one-time programmable memory? In fact, it has many, many uses. Some of the key ones we'll discuss in this chart. So let's start with our edge nodes and hub aggregators and network access. All of these things require secure communication. This drives the need for data protection and encryption schemes that in turn require memory for storing secure keys. Edge sensors and signal conditioning circuits also need calibrating, trimming, or setting up, while the controllers need secure code storage for data or for boot. In all of these applications, OTP brings several advantages over its NVM alternatives. Let's take a look at a couple of key markets where OTP is used extensively. Okay, a quick question. Raise your hand if you have a smartphone. Okay, that looks like that's most of you have raised your arms. I hope you're not looking at your smartphone right now, by the way. So what I can see that most of you have a smartphone, and I think that goes for most people we know. So just from our personal experience, it would be difficult to deny that the smartphone market and the market for tablets and phablets is simply huge, and it represents a tremendous opportunity for all of us. For vendors of OTP, it gets even better, since there are over 20 instances of OTP in your average smartphone. And as we add more sensors and functions, this number will only grow. You can read the list. This is just some of the things: battery chargers, display controllers, touch controller, RF stages, application processors, baseband processors. If I've missed anything, just let me know. A recent teardown of the Apple iPhone 6 Plus by those good fellows at Tech Insights shows a BOM cost totaling $242.50, very precise analysis. $116 of this is for IC content. It also shows more than 25 different major ICs on the main board, many of the components similar to the ones on our list. Nearly all of these devices on the phone have a need for OTP for the applications we discussed before, storing trim, configuration, secure keys, or calibration settings. A particular favorite for OTP is the PMIC, the power management ICs. PMICs have evolved from standalone voltage regulators and supply voltage supervisors into highly integrated programmable microcontroller-based SoCs. And there's multiple PMICs in every smartphone, in fact, in every smart connected node. PMICs take care of the many tasks required to manage today's complex power schemes, like power sequencing, DC to DC conversion, power source selection, voltage regulation, and most importantly, battery life optimization. OTP provides a real source of competitive advantage for PMIC suppliers, since it allows them to develop a platform solution that may be easily customized to suit either application or customer-specific requirements. Mass customization, if you like. How does this work? Well, customers first evaluate the PMIC in their application, then feed back the required defaults. These defaults then are programmed into OTP by the PMIC supplier at device test. Okay, the next application. I know this is a car, but you can't get away from the fact that it's actually mobile and it does have a battery, and increasingly there will be battery operated. So I think it does fit into the smart connected universe. In the typical automobile, there are dozens of subsystems and hundreds of devices that can use OTP memory. Automotive is growing at around 11%, and it's actually showing faster growth than the combined smartphone phablet market, representing an IC market size close to $23 billion. Today, electronic components make up more than 30% of the production cost of a car, and market experts predict this to reach 50% by 2030. The typical car today includes electronic modules for engine control, safety monitoring, rear-view cameras, entertainment, and navigation and power management. With the future trend to more connectivity and to more automated driving, the complexity and number of semiconductor devices will increase, along with the critical requirements for safety and security. The driverless car is not too far away, with testing or development underway at Volvo, Google, and Apple, amongst others. Did I really mention Volvo, Apple, and Google in the same sentence? Yes, the future is going to be a whole lot different for those guys in Detroit. With this level of connectivity and automation, many of which are safety critical, security just cannot be compromised. Having a hacker steal your credit card details is quite painful, but having a hacker gain access to your braking and drivetrain systems in your car could be, quite frankly, deadly. Okay, so maybe this is a stretch, but who would imagine just a few short years ago that employees would be bringing such a wide range of personal electronic devices into the workplace, especially with the blessing of their corporate IT department? Okay, so let's now have a look at some of the requirements placed on OTP within the smart connected universe. This slide shows some of these demands. We will discuss each of them in the following slides. The first one is cost. Cost is often the determining factor in market adoption. Having great features is not enough if the cost point is not right. Cost contribution from an OTP perspective can come in many guises. Area is the most obvious one. To test the time for programming, perhaps less obvious. Sidense OTP cells use a single transistor per logic bit in single-ended read mode. This minimizes the area of the macro and obviously has a direct impact on wafer cost. Furthermore, embedding Sidense OTP memory on chip does not require any additional processing steps, masks over a standard CMOS process. OTP allows chip makers to go to market early and progressively iterate trim, calibration, and configuration parameters until their performance goal is met. This provides considerable cost saving since these iterations do not require a mask change, for example, using ROM, which would be very expensive. Once the performance goals have been achieved and the code is stable, parts of it or all of it may actually be converted to ROM. Once you've converted OTP to ROM, then that eliminates the programming. So again, you can have a reduction in programming time, which equals cost. All of these factors contribute to the cost effectiveness and lower risk of using a 1T OTP solution. Okay, let's have a look at reliability. Sidense OTP macros undergo a very comprehensive and rigorous qualification program. Qualification typically follows JEDEC standards and foundry standards like TSMC 9000. Sidense develops test chips that are manufactured in the target fab process and typically include all macro blocks covering a range of macro sizes. Characterization is performed on slow, typical, and fast split lots, typically over 3 manufacturing lots, in order to cover all possible processing variations. Qualification tests include data retention storage life, high temperature operating life, high temperature storage, and time-dependent dielectric breakdown, TDDB. The TDDB test determines the memory retention characteristics and is often used as a proxy for PPM. The retention for Sidense OTP macros exceeds 10 years at a maximum operating temperature and at 100% read duty cycle. Sidense also offers an automotive package with testing and compliance to AEC Q100 grade 0, and also some specific vendor testing like PPAP, which is Production Part Approval Process Standards. These often include higher temperature testing at 150 degrees C and higher, and also additional services like DFMEA. Okay, let's have a look at low power operation. The proliferation of wearables is making low power consumption even more critical than ever, often in determining the viability of a product. Battery life, as we all know, can be a deciding factor when selecting your next smartphone and now your next smartwatch. Low power is not just important for customer products, but a vast array of medical and health monitoring devices, where in the case of an implantable device, battery life becomes a quality of life issue also. It is no longer just about batteries, since many forms of energy harvesting are now being investigated, and in some cases these are actually being used. As alternative sources of power, these include indoor light, RF, thermal energy, looking at ambient gradients of body temperature, for example, friction, and skin alkaline. As a matter of interest, and I did use Wikipedia for this fact, I apologize. As a matter of interest, the average adult generates 50 to 150 watts during 1 hour's vigorous exercise. There's a fact for you. Imagine how the world would change if that was the only way to power your smartphone. These forms of power require many clever power-saving techniques, including special low-power design tricks, sub-threshold design circuitry, power gating, and distributed processing. And this requirement, as I mentioned, is not just limited to wearables and consumer products, but industrial products also. Let's consider a remote SCADA industrial sensing application found, for example, in the oil field. In this situation, pipeline sensors send information wirelessly back to control centers that may be hundreds, if not thousands of miles away. Sending a service technician out in the middle of the night to the middle of Alaska just to replace a couple of AA batteries would be quite expensive. Fundamental to low-power design is the fact that Sidense antifuse bit cell does not consume DC current in a steady state, except for minimal leakage. However, as we have seen, there's more to the OTP than just a bit cell. The OTP power consumption of its supporting circuitry, its sense amps, multiplexers, decoders, interface circuits, etc., need also to be considered. Sidense OTP provides users with several power-saving modes that minimize power in both an active and inactive states. One such mode allows the OTP to be powered down immediately after its contents have been read during boot up. It's then in a very, very low power mode, resulting in nanowatt power consumption. To minimize power during read, the active state, the user may operate in differential or redundant read modes. As well as the low power requirement, it is often necessary to read OTP contents during low voltage conditions. Such conditions may be experienced at boot up when the supplies have not yet reached their steady state, low voltage sources, or just due to a decaying, aging battery. Under these conditions, operating in differential or redundant modes would be recommended again. Some newer designs feature read assist modes that integrate charge pumps directly into the bit or word line that boost the read voltage. Using such techniques allow read voltages close to core voltages. Okay, security. Mentioned this a couple of times already, but security is a growing concern for the smart connected universe. Why? Well, many nodes have internet connection. Many nodes are left unattended 24/7, and also maybe, in the case of industrial sensors, maybe remote. This gives your dedicated hacker plenty of time and opportunity to hack. Imagine the old days when people could tunnel through into the network via networked printers. Well, this is going to scale on an amazing situation when you look at all the smart connected devices out there. Again, since the Sidense bit cell does not depend on charge storage to determine its state, it is inherently more physically secure than charge-based technologies, such as used in flash memory. Furthermore, programming cannot be undone by exposure to high temperature, voltage, or radiation. Also, determining the logic state of the bit is difficult to detect using commonly available reverse engineering techniques. Furthermore, our macros employ several tamper-resistant techniques, built-in redundancy and error correction. All of these further enhance security. Differential read mode and power signature masking techniques are also used to foil any power analysis attacks. And finally, program locks negate attempts to maliciously program the macro. These locks can lock down the whole macro, sectors, or just rows. Okay, flexibility is key. So if you look at a single OTP macro, it can be actually petitioned for many, many different purposes. For example, you can petition it by user case or memory size, or use it as an EMTP or provision as ROM. Each petition may operate in a different read mode. The example shown here is a 4K by 16-bit OTP macro, 64K bits in total. It comprises 8K bits of emulated MTP, we'll have more of that on the next slide, 8K bits for differential read. You're using differential read mode in this case to provide added security and a lower read voltage. And then 16K bits in single-ended mode. We're using this for faster programming during test and to minimize the macro size. And then finally, 32K bits at the bottom, the gray section there. This has been converted to ROM. So the code is stabilized, and we're converting it to ROM to eliminate the programming cost. Okay, so let's have a look at EMT, emulated multi-time programming, a little closer. EMT allows for a few programming iterations of code, data, and configuration. It's no real secret that EMT really is multiple instances of a single OTP bit cell. But since the Sidense macros are very small, designating multiple bit cells for future programming is actually quite economical, particularly for smaller macro sizes. No erasing is necessary since the data is programmed into the next available reserved space. The OTP controller that we saw in the previous slide takes care of the memory indexing, etc. Okay, specialty process support. Sidense is a world leader in BCD, HV, high voltage variants. We have over 90 customer projects licensed for these technologies, and more than 11 and are available in more than 11 nodes at more than 5 foundries. In these nodes, Sidense boasts a macro area that is 2 to 4 times smaller than competing solutions. The inherent stability and reliability of Sidense technology over a wide temperature range supports applications such as power management chips, display drivers, and image sensors. Sidense OTP in these processes has been adopted by many leading chip suppliers and is designed into many of the smartphone chips we discussed in the previous slide. Portability and scalability. The universal acceptance of Sidense OTP makes for quite a challenge, particularly for us guys at Sidense. The diverse range of chips with many different requirements from high performance logic through precision analog to BCD means that the Sidense OTP has to be qualified in a wide range of nodes and voltage variations. Furthermore, this OTP needs to be available in a wide range of foundries and also IDM processes. Sidense has a broad portfolio serving over 15 foundries and IDMs in over 55 different processes. This chart shows the node feature size on the vertical axis and the process I/O voltage on the horizontal axis. Sidense product families are shown in the boxes. Sidense supports nodes from 180 nanometers through to 20 nanometers and has FinFET developments at an advanced stage. Process I/O voltages range from 1.8 volts for the advanced nodes to 12 volts and higher for 180 nanometer products. I'll not go through each of the product families, but I will mention just the SLPX and the SLPMX. These are recent developments available in 130 BCD and designed specifically for the demanding needs of the power management IC and MEMS sensor market within the smart connected universe. These products offer options for high-speed read and programming for higher density code storage applications, or single supply and low voltage read operation for the lower power, lower density applications. For the advanced nodes, 40 nanometers and beyond, including FinFET, requiring I/O voltages at 2.5 volts and below, Sidense developed the SHF memory system, subsystem. So where are we headed? Perhaps this cartoon gives us a clue in the smart connected universe. The truth may be stranger than fiction. I hope nobody was offended by this joke. So let's quickly summarize. The smart connected universe represents a huge opportunity for chip suppliers and OTP IP vendors alike. While there are many challenges like power, size, and security, there is little doubt that this is the next big thing. In fact, representing not one killer app, but many. Of the many NVM choices out there, OTP represents a cost-effective and reliable solution for many of the applications. And finally, the Sidense solutions, by meeting these challenges, provides you with a possible source of product differentiation. Okay, that concludes the presentation, and I thank you for your time, and I'll hand you back for Sean that I believe may have some questions and hopefully some answers.
Yes, thank you so much for everyone attending today's webinar. We do have a few questions already online, Andrew, and if we don't get to your question, please contact Andrew at Faulkner@Sidense.com. Also, you can be sure to check out Sidense and its 1T OTP memory products at Sidense.com. Andrew, the first question is, has 1T OTP been tested and approved by any security labs or agencies?
Okay, that's a very good question. Yes, obviously specific details are confidential, but Sidense technology has been evaluated both by third parties, groups like NDS, and also at our customers.
The second question is, can 1T OTP work with FinFET transistors?
Oh, okay, yes. I just got back from the TSMC symposiums last week, and so FinFET was definitely a topic for discussion. So the answer is yes. 1T OTP scales exceptionally well to FinFET processes. In fact, it uses the same bit cell design that we use in all of our OTP products, so it's well understood and well known. In fact, also, it performs better than 28 and 20 nanometer planar technologies. It provides considerable wider margins between a programmed and unprogrammed state. It has lower leakage current and offers about a 40% reduction in comparable macro sizes. So, yes, we've seen some very good performance for our FinFET designs.
Next question is, could 1T OTP be made into a standalone memory chip?
Absolutely, and some vendors do offer these, but I don't quite know why you'd want to do that. The advantages from embedding it in chip are quite, as we discussed in this presentation, are quite numerous, from cost to security. So it doesn't make sense to have it external.
And finally, is this available for larger nodes, larger than 180 nanometer geometries?
Let me think about that one. That's a good one. Not that certainly Sidense doesn't offer anything for nodes greater than 180 nanometers. I'm not too sure about competition. It becomes less economical, or it doesn't make as much sense because the voltage, the breakdown voltage that you need to program the states scales with the geometry size. So, you know, for 180, you're already looking at kind of like 9 volts to program it. So if you go beyond that, you're looking at, 10 to 15, and it just doesn't make sense.
Okay, that's it. So for Andrew Faulkner, my name is Sean O'Kane with ChipEstimate.com. And once again, thank you for attending today's webinar on selecting NVM memory for the smart connected universe. Thank you, Andrew.